Hello and welcome to the group 1 of the periodic table, as known as the alkali metals, presenting to you by Sun, Tata, Meg, and Weave for 10 or 2. So let's begin with the trend in melting points. So as you can see from the graph here, the alkali metals show a downtrend with a declining melting point from 180 degrees for lithium to 98 for sodium and 63 degrees Celsius for potassium respectively. So why is that? Well, this is because of the increase in size of the atom as it goes down the periodic table. From lithium, a very small tiny atom, and when it gets slightly bigger when it comes to sodium, potassium, rubidium, cesium, and so on. So why is that again? Why does the size of the atom matter? Well, as the atom increases in size, from lithium to sodium to potassium, and so on, the distance between the nuclei and electrons also increase, which that would lead to the fall of attraction between the two, allowing each metal atom to be separate more easily when getting heat, or in a simple word, making it more reactive. So when you are heating something, or in this case the alkali metal, which is a solid, you are trying to cut those packed and tight molecules of solid into pieces to separate those molecules apart from each other as they get melt and turn into liquid. And according to the diagram, you are essentially cutting the valence electron or the outermost one, which it is much easier for you to cut the potassium molecule apart compared to lithium because there's less attraction between the valence electron and the nucleus, thus leading to the earlier melting points as the metal atoms get bigger. So now I pass it on to Meg so he can describe to you the trend in density.
Next, I'll be talking about trend in density in alkali metals. Alkali metals have pretty low density, and all these three metals, which are lithium, potassium, and sodium, have density below water. Alkali metals have the smallest ionization energy, making them have low density. The atoms are packed in the same formation, which means that the density is dependent on the number of atoms in their given atomic radius. The size of the atom increases down the group, and the volume of the atoms also increases, making the density trend upward. As you can see from this diagram, potassium have an abnormal increase in both size and mass, making it an exception from the trend in density. And from this diagram, you can see that this is an example of the sodium having the smallest ionization energy, which means that it requires less energy to remove the valence electron since there's only one electron in the valence shell.
Now I will be talking about the trends of reaction of alkaline metals in water. We first begin by talking about lithium. Once lithium is in contact with water, the lithium floats to the top of the solution and fizzles until it completely disappears. The solution produces lithium hydroxide, which dissolves within the solution as hydrogen escapes. It is possible to test the presence of hydrogen by using the flammability test. The process is exacted by trapping the gas partially within the test tube and lighting the test tube up, equating the flames throughout the test tube internally. Once lithium hydroxide has been produced, we are able to test its presence within the solution by adding phenolphthalein. Phenolphthalein is a base and acid indicator which is applicable to every group 1 alkali metal. Once added to an acidic solution, in this case the solution will stay colorless, and if it is a base solution, it will turn into a red-purple color. In the case of lithium, a base solution, it turns into a red-purple color. Now moving on to sodium. Sodium produces a much more rapid reaction as sodium forms into a ball-like shape while subjected to the movement around the water surface due to the formation of hydrogen. The reaction is more exothermic in comparison to lithium. Therefore, the metallic sodium is completely melted. It also may occur that a slight flame is present before it completely disappears. This process produces sodium hydroxide and some hydrogen gases. Finally, once potassium is added to water, it ignites almost in an instant. The exothermic reaction in comparison to sodium is turned up a notch. This results in the production of potassium hydroxide and hydrogen gases. So now on to the explanation of how this all occurs. Well, since the characteristics of most alkali metal is the ability to displace the hydrogen present in water, therefore allowing the metal to oxidize, which in this context is the removal of electrons from the alkaline element. After oxidizing, the element is left as a metal ion, and the water forms the hydrogen gas and hydroxide ions. The formula is written as follows on the screen. These are the points that affect the reactivity of group 1 element and why it increases as you go down the group. First reason, because the atom gets larger as you go down the group. Secondly, the outer electron gets further from the nucleus as you go down the group, making the attraction between the nucleus and outer electron weaker, so the electron is more easily lost, thus a more rapid and violent reaction.
Comparison with heavy metal. So the one we'll be comparing today is the alkali metal and the transition metal, and we'll be comparing the properties. So the property for the alkali metal, it is a soft metal, big metallic bonding and low density melting point and boiling point. Meanwhile, for the transition metal, it is the exact opposite, which is a hard metal with high density melting point and boiling point, which it can be seen from this table shown here. It shows that the alkali metal having a melting point that didn't exceed 1000 Celsius, and also the boiling point that exceeds 1100 or 200. Meanwhile, for the transition metal, the melting point reaches up to 1000 for the majority of it, and also the boiling point that reaches up to 2000 to 3000 for the majority of it also. For some of that difference previously, it might be from the electron configuration. The alkali metal has a ns1 electron configuration, which means that there's one electron on the outest ring, which is lower when compared to the transition metal, which usually has a 3dn electron configuration, with a few exceptions such as 4s1 and 4s2. This led to the alkali metal having a low metallic bonding and inefficiently packed, and it resulted in having a lower density, melting point, and boiling point.